Alright, so I don't know what you're feeling now, but when it was my first time to learn the KKT condition, it's difficult. So let's use some examples to show how it may be used and what's the things that we may obtain after we apply the KKT conditions. So let's consider this example. So there is a story here. There's a retailer selling products 1 and 2. So this retailer is selling 2 products, okay? And the retailer need to set supply quantities Q1 and Q2 for each product. Once we do the choice, then the market clearing price for product I is going to be PI, which equals AI minus BIQI. So I hope this makes sense to you. If you push a lot of products onto the market, then there will be not so many people who want to pay a high price for that. So if you are going to sell everything, the price is going to be PI, okay? Something like that. So your PI is going to be a downward sloping line as a function of QI, where your AI and BI are known parameters. The retailer sets Q1 and Q2 to maximize its total profit, and there is a constraint. Your total supply, Q1 plus Q2, cannot be greater than K. That may be due to the capacity for the shipping truck, the capacity for your warehouse, the capacity of operations, whatever. But there is a constraint like that. We're going to formulate the retailer's problem, take a look at convexity, try to solve it, of course, with the KKT condition, and try to get some economic intuitions or interpretations. For example, how do our optimal quantities change with K, and what does that mean? Okay, so first we need to do some formulation. Our formulation would be here. We want to maximize the total profit, which is the sum of 2 profits. And for each profit term is quantity times your sales price. We don't have cost here, so let's ignore the cost information. Then in that case, each dollar you sell, each dollar you earn. That's profit or profit margin. Your constraints is that your Q1 should be non-negative, Q2 should be non-negative, and your Q1 plus Q2 should be no greater than K. So that's your formulation. Let's take a look at convexity. So the easier part is that, okay, constraints are all linear. So this is a linear feasible region. That would be convex, of course. Then for the objective function, let's say it is negative f, or we say f is your negative objective function. Okay, then we may do gradient, we may do Hessian. The Hessian would be this one. And very quickly, we may see it is positive semi-definite because your BI is greater than 0. Or if we are more aggressive, this is actually positive definite because B are positive. Okay, so anyway, this means that our objective function is convex or strictly convex. So the whole thing here is concave, because we are talking about the negation of f, okay? So as we are maximizing a concave function subject to linear constraints, this is a convex program. That's good. However, if we try to do the first order condition here, this may be infeasible. Why is that? We do know that A1 and B1 are all positive. So this Q1 and Q2, they are not going to violate your non-negativity constraints. But of course, the sum of them may be too larger than your K. If that's the case, then we don't know what to do. So we now need to rely on the KKT condition. So to apply it, our Lagrangian should be first derived. So this is your original f. This is your g, or I should say b minus g, okay? This is k minus q1 minus q2, because originally it's q1 plus q2 less than or equal to k. So we use the bigger side to minus the smaller side to get this one. And that allows us to set our lambda to be non-negative to reward feasibility for this maximization problem. Okay, and then if we set the gradient to be 0, what does that mean? We're going to differentiate the Lagrangian with respect to Q1 and Q2. So you don't need to differentiate that with respect to lambda, because you are trying to find x1 and x2, I should say Q1 and Q2, to try to do this maximization. So only Q1 and Q2 are variables. Okay, here I write the Lagrangian as x. It's just an abbreviation for all kinds of decision variables, but you know it's Q1 and Q2. Alright, so once we do that, it should be not too difficult. For the differentiation, first, if you do it here, it's going to give you A1 minus 2 B1 Q1. But you also have a term here, so that's how you get this negative minus. For Q2, it's pretty much the same. So now we know there are two possibilities. For you to find a lambda to satisfy the KKT condition, your lambda must be non-negative, right? So your lambda should be either 0 or positive. If your lambda is 0, okay, then in that case, you only have these two terms as your original unconstrained problems. Then your Q1 and Q2 would be here. Q1 is A1 over 2B1, Q2 is A2 over 2B2, just as you have no constraint. This would be an optimal solution if your primal constraint can be satisfied. Okay, so that's one possibility. Or it's possible that actually this is not allowed, this is not true. Then you know your lambda is going to be positive. If that's the case, first we know because lambda times the primal slack must be 0 due to complementary slackness. So your Q1 plus Q2 must be equal to K. If that's the case, then you have constraint equality 1, equality 2, equality 3. Solving these three equations would give us your solution of Q1 and Q2 as a function of a few complicated terms, but I hope this is not too difficult for you and you may want to try it by yourself. You have three equalities with Q1, Q2, and the lambda as unknowns. So you may do some high school arithmetics to get a solution here. Okay, once you do that, when will this be an optimal solution? Obviously, it's when this ideal solution is invisible. Okay, so that's how we solve this problem by the KKT condition. So let's do some arrangements, and we may write down your optimal solution in this complete way. Your optimal solution is expressed as Q1 star and Q2 star. They have two possibilities. If this following condition holds, then your optimal solution is here, otherwise it's there. So don't forget the way to write down your complete optimal solution. You have several conditions. In this particular case, your optimal solution is this one. In that particular case, your optimal solution is that one. So you need to somehow list all possibilities and list all the optimal solutions under all possibilities so that your solution is really complete. Okay? You cannot just give this one or that one. That's not a complete solution. So with this, actually, we may learn something. For example, when K increase, we actually can see that Q1 and Q2 will weakly increase. Why is that? When your K is very large, then in that case, you're going to have no impact on your optimal solution because K is already too large, and your optimal way to balance demand and supply has nothing to do with K. So in that case, your K has nothing to do to your optimal solution. But if your K is small, then when you increase K, you're going to order more because previously you want to order a lot, but because K is small, so that's why you order this amount. When K becomes larger, you're going to order more. So K really positively impact your order quantity. That makes sense. This economic intuition makes sense. Graphically, suppose A1 is Q1, B1 is B1 is B2, then we may see that when K is large enough, K has nothing to do with your Q star. But when your K is small enough, then when K increase, your order quantity would also increase, which is something we just mentioned. So this is one example of using the KKT condition to solve the problem, solve a nonlinear program analytically, and get some implications.